name is Nola Charles, and this is for Physics 2211. The focus of Lab 2 was to analyze the projectile motion by capturing video data and comparing it with a computational model. The computational model is based off of Newton's second law, where we altered the force's presence to see the impact of the projectile. The main result of the lab was how the projectile of the experimental data reached a lower velocity and it had a shorter range than the computational model that did not account for drag or air resistance. Thus, our result demonstrates how the presence of drag force in addition to the force of gravity has a significant impact on the outcome of the projectile. The lab simultaneously demonstrates Newton's second law by demonstrating how the motion of the projectile is governed by the net forces acting on it. The system for my lab was the paper ball, while the surroundings were my hand at the table, air, gravity, and other external forces. The Newton's second law can be demonstrated by the momentum principle shown on the left, where the net forces should always equal the change in momentum over the change in time, where P represents momentum, or mass times velocity, over time. The formula can be further derived to form what is called the velocity update formula, which we use in our computational model to update the velocity and positions of the trajectory to plot and analyze against our experimental data. For net force, we use the formula on the right, which sums the force of gravity and the drag force, represented by B, the drag constant, multiplied by velocity squared times its unit vector. These are the steps that we will be taking. This is my video that we used in the program. This is my tracker data. The object's initial position and velocity are measured and set in both tracker and the GlowScript models. I found the initial position through the tracker program by using the meter stick in the back of the video as the basis and starting the tracker at the moment the ball left my hand. This was equal to 0,1.78, 0 meters. For initial velocity, we used the average velocity formula of the change in position over the change in time between the first two data points. This was equal to 0.7, 1.8, 0 meters per second. For initial time, we used the timestamp when the ball left my hands, 0.7 seconds. For my computational model, we edited the code and we put in the tracker data. We plugged in the mass of the paper ball, the initial conditions mentioned previously, and the gravity constant. We did one more model where we accounted for drag, and we did one where we did not. This is highlighted in the blue line. To find B, the unique drag constant, we used the guess and check method until we yielded a projectile that mimicked the experimental data. This is a continuation of the velocity update formula loop that we used to find the position components as explained earlier. Next, I generated a spreadsheet in Excel to compare the X and Y positions components over time. This allows for us to analyze the velocity of the trajectories by analyzing the slopes. The blue data is our experimental data generated from the tracker program. It has extra columns in the other data to account for the conversion of centimeters to meters. The orange data represents my computational model accounting for only gravity. The green data represents my computational model accounting for both gravity and drag. Emphasizing the role forces have on motion, aka Newton's second law, our data demonstrates how having more applied forces such as drag shortens the trajectory's range and lowers the terminal velocity, or the velocity in general. This can be seen in how the orange graph only accounting for gravity has a higher peak and a wider range than the experimental data, the blue data, or the computational data accounting for both drag and gravity as applied forces. This also offers a chance to talk about experimental error, human error, as in how the green line is supposed to perfectly mimic the blue line, but it does not. As far as our what-ifs for the first question, terminal velocity is the maximum velocity an object can reach when falling through air due to the balance of forces acting on it. Graphically, this will look like the slope decreases linearly, demonstrating how the forces have been balanced. My graph of gravity and drag demonstrates this when it becomes slightly linear before hitting the table, showing how the drag force and gravity are temporarily balanced. For question number 2, this would take shorter if the object was initially thrown straight up. This can be proven through the equation shown earlier for drag, since how throwing it straight up would experience an increased drag constant, increasing the overall drag force, making it have a shorter trajectory and hit the ground sooner. However, this would be extremely minimal and probably unnoticeable due to the minute differences it would make to the drag force. Thank you so much.